Today I'm just going to go over some examples of how to prove whether or not an operator is linear, as well as how to find the eigenfunctions of an operator and the associated eigenvalues. The two properties that we're going to be looking for an operation to be linear is essentially the distributive property, essentially that the operator acting on a sum of two functions should be the same as the sum of the operator acting on each function individually. The second property is essentially associativity, which is that if we apply our operator to a number times a function, it should be the same as if we first operate on the function and then multiply by the number. A couple things to clarify is that in the second rule, the number here can be complex valued. It doesn't have to be a real number. And in fact, it can even be other kinds of numbers, but whatever. The other thing is that in general, we operate on functions from the left. So I've always written my operator on the left. And we don't really usually write things like L of f of x, which is, I write f of x is equal to, x squared. And what that means is it takes x and it turns it into x squared. And that's really what an operator does to functions, but the notation is just a little bit different. I don't write L of f of x, I write L operating on f of x. It would be kind of like if I wrote f of x as fx equals x squared. So just so you understand the kind of difference in notation. But it means something very similar in terms of, in each case, we're taking one thing and transforming it into a new thing. But a thing of the same class, right? So f of x takes a number and turns it into a new number, whereas an operator L takes a function and turns it into a new function. Let's start with a couple examples. One such example can be the complex conjugation operation, which I'm going to represent by a sort of capital C. And I'm going to put these little serifs on it just to distinguish it from, for example, the number over here. And this operation on a function, it turns our function f of x into the complex conjugate of f of x. So let's consider our first condition. If I apply my complex conjugation operator to the sum of two functions f of x and g of x, well, we already know how the complex conjugation works, and if I take the complex conjugate of a number plus another number, it's just the sum of their complex conjugates. So this is, in fact, f of x complex conjugate plus g of x complex conjugate. They don't really affect each other independently, and so this one checks out. Now let's look at the second requirement. If I apply the complex conjugate operation to a number, I'm going to call it a, just so we don't deal with capital and lowercase c, times f of x. Well, when you take the complex number of a product of one number with a second number, you get the complex conjugate of the first times the complex conjugate of the second. And this is not equal to a times the complex conjugate operator acting on just f of x. Because on the right-hand side, we have a times the complex conjugate of x. And so we see that when I apply the complex conjugate to the product of a with f of x, I get the complex conjugate of a times f of x. And when I apply the conjugation operator first and then I multiply by the a, we're left with just a times the complex conjugate of f of x. And so this second condition does not apply. And so this complex conjugation operation is not a linear operator. So this just goes to show that there are a lot of operations that we use all the time and they're very useful, but they're not linear operators. And that's fine. Linear operators have particular properties, which makes them useful for certain things, but other operators are still very useful in other ways. Now let's look at a different operator. For example, how about an operator that rotates functions by 180 degrees? Graphically, that's easy to represent. For example, imagine a function like this. If we apply our rotation by 180-degree operator to it, our function is going to end up looking like this. Mathematically, what we've done is we flipped our function over the y-axis, and then we flipped it over the x-axis. So we reversed x and y, which we can represent as this expression. So I'm going to represent my rotation operation by r with a subscript of 180 degrees. And in this case, first I flip it across the y-axis, which means I flip the sign of x, and then I flip the sign of the whole function, and so I apply a negative sign out front. So now let's test the two different conditions required to be a linear operator. So the first one is if I apply my operator to f of x plus g of x, well, this just flips the sign of f and of x, and it does so in both cases. And this, on the right-hand side, is the same thing as our rotation operation applied to f of x independently from the rotation operator applied to g of x. So this first expression, once again, checks out. So now we need to check the second condition. Multiplying our function by a number just scales our function, though. It doesn't really change its overall behavior. And so when I rotate it by 180 degrees, it's just going to remain scaled, but it's just going to be flipped. And so this simply gives us negative c f of negative x, and that can also be expressed as c times the rotation of our original function f of x. And so this time around, the second expression, the second condition, is also met. And so this rotation by 180 degrees is, in fact, a linear operation, which is to say that if I apply it to multiple functions at once, it's the same as if I apply it to each of them individually and then add it all together. And also that if I scale my function before the operation, it gives me the same result as if I scale the function after I apply my operation. Before we move on to talk about eigenfunctions and eigenvalues, I'd like to actually go over an example where this first expression isn't satisfied, because so far both of them have. So let's consider yet another one. For example, an operation, which I'm going to call s for square. It takes a function, it takes an argument, and it squares it. So now let's look at how this holds up with the first rule. So if we apply this square operation to f of x plus g of x, is this equal to our square operator applied to f of x plus our square operator applied to g of x? I think you can probably see already that it's not. On the left-hand side, this gives us f of x plus g of x quantity squared. And the right-hand side simply gives us f of x squared plus g of x squared. And we're going to end up with this pesky cross term on the left-hand side, and so these two sides are not equivalent, and so this last example fails the first condition needed to be a linear operator. And in fact, it also fails the second condition. Okay, so now let's talk about eigenfunctions and eigenvalues. First of all, let's talk about where this funny word comes from. What is eigen? This comes from German, and eigen means self or own. Not like you owned a 12-year-old in Fortnite or Call of Duty, but own as in belonging. In math, what we really mean by this is characteristic, which doesn't necessarily follow immediately from German. There's some contention about that, but that's really what we mean by this. We mean an eigenfunction of an operator is a characteristic function of the operator. The function itself tells us something about the operation we're performing. The mathematical definition of this is that if we apply a linear operator to a function and it returns the same function just scaled, just multiplied by some value, a number, possibly a complex valued number, then that function is an eigenfunction of the linear operator. The scale factor c is special in its own right. Just like how the function f of x is characteristic of the operator, this scale factor c is characteristic of the function f of x. It tells us if I apply the operation to my function, how does my function change? C in this context is referred to as the eigenvalue of the eigenfunction of the operator L. I should point out that any particular operation can have many eigenfunctions. To see that, let's actually work through an example. Let's return to the rotation by 180 degree operator that we were talking about earlier. To find the eigenfunctions of this operator, what we want to do is we want to say that when we apply our rotation by 180 degrees to our function, it should be equal to nothing but a number times the original function. And so that implies that negative f of negative x must be equal to a number times f of x if f of x is to be our eigenfunction. This is not always going to be true. For example, consider the function x plus 1. That gives us x minus 1. And x minus 1 is not just a number times x plus 1. If we graph this, you'll see that we've taken the function x plus 1, a straight line with a y-intercept of 1, and we've actually translated it, we've shifted it downwards. And because this function wasn't just rescaled, but also translated or shifted, it's not an eigenfunction of our operation. So what is, or rather in this case, what are? If f of negative x is equal to f of x, in other words, if f of x is an even function, then c is just the number negative 1. Well, how cool is that? In just a few seconds of work, we didn't just find one eigenfunction of our rotation operator, we found an infinite number, the entire set of all even functions. Not only did we find all these infinite number of eigenfunctions of our operator, but we also found the eigenvalue of every single one of them. It's the number negative 1. Well, we found an infinite number of eigenfunctions of our operator, but have we found all of the eigenfunctions of our operator? So let's consider another example. Let's consider all the functions that are odd. If we apply our rotation operator to one of these odd functions, then we find that we get negative f of negative x as usual, but f of negative x is just negative f of x, and the negative signs cancel out, and we're left with f of x. In other words, this satisfies the relationship that our operator applied to our function is equal to a number c times f of x, where c, in this particular case, is just the number 1. Since any odd-valued function satisfies our eigenvalue equation, that means that all odd functions are eigenfunctions of our rotation by 180 degree operator with eigenvalues of plus 1. What this means is that even functions and odd functions are left relatively intact by this rotation by 180 degrees. So let's analyze this in a little bit more depth. What does it mean to be intact, if you will? That is not a technical term, by the way. And what is the significance of the negative 1 eigenvalues for our even functions and the positive 1 eigenvalues for our odd functions? Once again, let's consider a graph of, in this case, let's just pick an arbitrary even function. If I apply my rotation operation to this function, I'm going to end up with something like this. At this point, you might say, I don't know about you, Mr. Lunny, but that doesn't look like the same thing I started with. You're kind of right, but if you think about it, this blue flipped function is really just the red function where I've multiplied every single point by negative 1. I've scaled it by a factor of negative 1. If I scale something by a factor of 2, it's going to stretch out by a factor of 2. If I scale something by a factor of negative 2, it's going to flip and stretch out by a factor of 2. If I scale something by a factor of 0, it will simply become a horizontal line. And so we can scale something by a negative value, and all that implies is that in addition to whatever stretching we're doing, we're also going to flip it over the axis. The fact that the eigenfunctions in this case are negative 1 implies that we are flipping it, but we're not stretching it. If we do the same kind of analysis for our odd functions, we'll end up with something that looks more like this. All that's really happened is I've changed its color. It turned blue. That's because the eigenvalue in this case is positive 1, which means I'm scaling my function by a number 1. Well, if I multiply something by 1, I'm not changing it. So my even functions get flipped. They don't get stretched, they only get flipped. And my odd functions don't have anything happen to them at all. So let's take a look at what would happen if I have something that is neither even nor odd. When we rotate this one by 180 degrees, we find that it's not so easily related to the original function that we started with. Clearly, they're 180 degree rotations of each other, right? That's how we did it. But mathematically, if I want to get from this red function to this blue function, I have to do more work than I had to do on either of these on the left-hand side. On the top left, all I needed to do is multiply by an overall -1. On the bottom left, I had to multiply just by 1. I don't do anything at all. But over here, again, first I have to flip the sign of the x values everywhere, and then I have to flip the result of that. I have to do a more complicated relationship. And so this function is not characteristic of the operation that we're doing, because it is changed in a more fundamental way than our eigenfunctions, which are the even and the odd functions. So we can think about eigenfunctions like this. A function is an eigenfunction of an operator if the operator only rescales the function. And the eigenvalue associated with that eigenfunction tells us how the eigenfunction is scaled. This might all sound like a lot of new fancy words to say very little, but this is actually a really powerful concept. For example, if you were to give me a list of every single eigenfunction along with each eigenfunction's eigenvalue of an operator, I could figure out what the operator is. So it goes both ways. If I know the operator, I can find the eigenfunctions and eigenvalues. But if I know all the results of the operation, I can reverse engineer what that operation has to be. And there's only going to be one unique operation that will work. So why do we care about all of this in this class? Well, if you think back to when we were talking about vector spaces, we established that functions can be thought of as vectors, and the space of all functions can be thought of as a vector space. In other words, everything that we've just talked about involving functions can be generalized to apply to vectors in general. It's just if we're talking about vectors in this context, we would say that a vector that is only rescaled by a particular linear operation is an eigenvector of the operation rather than an eigenfunction. Here's a pretty cool demonstration of this in the context of vectors that I've shamelessly stolen from Wikipedia. This is an example of what's called a shear transformation. And in this particular case, that transformation can be represented from taking a vector with x and y components and mapping it to a new vector whose components are x plus ay and y. In other words, positions with positive y values are shifted in the positive x direction. Positions with negative y values are shifted in the negative x direction. And in both cases, scaled by some value a. So not all vectors are simply rescaled here. We can see that any vector that had no y component is actually completely unchanged. So these blue vectors represent the eigenvectors of this shear transformation. The blue vectors are unchanged. They are simply scaled by an eigenvalue of 1. On the other hand, vertical vectors, and in fact any vector with any vertical component, is not going to experience such a nice effect, right? This vertical vector over here is not just a multiple of itself over here on the right after we perform the transformation. And in fact, this vector is both rotated and scaled. I said I was going to convince you why we care about this in this class, and Mona Lisa is not really particularly relevant, but we've learned how to represent quantum mechanical states, or at least certain quantum mechanical states, as vectors. Well, quantum mechanical states are represented by vectors, and it turns out that measurements can be represented as operators. Like in the case of a Stern-Gerlach measurement, where we've got some source of particles with some kind of state over here, and then we have our actual Stern-Gerlach device, which is a couple different magnets where the magnetic field is stronger on one side than the other. That gradient of a magnetic field causes the wave function or the state of the particle to split into its two different components of spin along the axis, the measurement axis of our device. And the screen itself is really what constitutes our measurement. Until we actually measure whether the particle hits the screen here or whether the particle hits the screen here, our best description of this particle is a superposition of the two. And so the screen represents a measurement. The screen selects the piece of our wave function that we end up determining. For example, do we determine that the spin is h bar over 2 in the z direction, or negative h bar over 2? And that is what this quantity here allows us to represent. This is all still very abstract, but we will make it less so in the future.